Professor Pelton. This is Chapter 5, Section 5, performing function operations. So we'll be going through add, subtract, multiply, and divide, and composition operations of two functions. Okay, so we'll be using f and g for the generic names of the two functions. For these examples, we'll be using 5x for the f of x and x plus 2 for the g of x for the generic examples in this first page. Okay, so for the addition, we have f plus g of x, so we have f of x plus g of x, and it's all of f and all of g being added together, so you need to use parentheses around those. So if I distribute the 1 that's in front of each of these, that gives me 5x plus 1x plus 2, which gives us a final answer of f plus g of x equals 6x plus 2. Okay, second one, f minus g is going to be 5x minus x plus 2. Again, distribute the 1's first, so we get 5x minus 1x minus 2 for a final answer of f minus g of x is 4x minus 2. Okay. Third one, multiplication. Typically with multiplication, they might not put a dot in between for the multiplication. Then it might just write f and g, just like 5x is written as 5 times x with a dot or without a dot. Okay, so here we have 5x times x plus 2, parentheses important again, because again you're multiplying the entire thing, not just part of it. Not having parentheses completely changes the problem, because if you write without parentheses, the only thing that's going to happen is the x's will multiply but not the 2, so they're important. So we multiply that out, it gets us 5x squared plus 10x, and we distribute for a final answer of f of g of x equals 5x squared plus 10x. And you can put the singular dot in there if you want, but it's not entirely necessary. Okay? Alright. Next one, division. We'll move this down a little bit. So we have f over g, so that's 5x over x plus 2. Okay. However, you notice we have this part where it says g of x cannot be 0. Okay. Because you cannot divide by 0. That doesn't mean you plug in 0, that just doesn't work. Because if I plug in 0, clearly 0 plus 2 is 2. That doesn't make 0. That doesn't make any sense. G of x is the entire denominator. So what we care is that x plus 2 cannot be 0. So if I subtract 2, x cannot equal negative 2. Okay? Because if I plug in negative 2, make that a little less sloppy there. If I plug in negative 2, I will get 0 in the denominator, which cannot happen. So my final answer, f over g of x equals 5x over x plus 2, where x cannot equal negative 2. So this has a limited domain. You cannot plug in any number each you want. Negative 2 will not work. Okay, the last one, composition. The way you say this is f of g of x. So the little open circle means one's going inside of the other. So you can see that g is going inside. So if it's written in this notation, the second one is going inside. So if we write f of x, that's 5x, correct? But we're replacing the x with another function. So the x, okay, inside is going to g of x. The g of x was x plus 2. Okay, so we distribute, and we get 5x plus 10. So f of g of x equals 5x plus 10. So that's simply just putting one inside of the other. So one has to happen before the other. Okay? Alright, let's try a couple examples here. So in this case, this is our f, this is our g, and we want to do addition of the two functions. So we want f plus g of x. So f is 3 root x. and g is negative 10 root x. Those are like terms, so f plus g of x will give us negative 7 root x. Okay, so that is the actual function. So this also wants us to do a example, which is f plus g of 4. And what's a specific example? There are many values of x. This is just one example. So we get negative 7 root 4, which equals negative 7 times 2, which is negative 14. So f plus g of 4 is negative 14. So at 4, we're at negative 14 essentially. Okay, so the last piece here is it wants the domain and range of the function that we found. So domain and range. So domain is input, range is output. Left and right on the graph and up and down on the graph. So, you can just plug in anything, correct? So the things you look for are the things you can't be. Think it inversely. Don't think what you can be. That's infinite number of things. Think what you can't be. So you have to look for denominators and even radicals. So we don't have a denominator here, but we do have an even radical. And last time I checked, you can't plug in negatives because you're not going to be able to get a real number when you have a square root or a fourth root or a sixth root of a negative number. Therefore, this x has to be greater than or equal to 0. Okay, as a result, 0 to infinity is the domain. You can be 0, hence the bracket, but you cannot get to infinity. Okay, and the range is the output once you plug it in. So plug in negative 7 square root of 0 and negative 7 square root of infinity. Okay, you'll get negative 7 times 0, which is 0, and then this will just be negative infinity. Okay, so as a result, the biggest I can be is 0, and I'm going to negative infinity. So again, these go both left to right, least to greatest. So let's see, 0 to infinity and negative infinity to 0. Let's see what that looks like on a graph. So we'll graph negative 7 times root x. Okay. Alright, so we can see I have this little swoosh on the bottom here. So if we look as far as our domain goes, we start at 0. We start at 0, and it goes for infinitely this way, right? So therefore, that is the 0 to infinity for domain. And the range, it also starts up here, but goes down forever, right? So that's negative infinity to 0, right? Least to greatest. That's our range. That is our domain, as you can see from the graph, because all we have is this thing right here. Okay? That is the end of part 1.